Today, we are presenting our work on self-supervised predictive coding with multimodal fusion for patient deterioration prediction in fine-grained time resolution. In the emergency department (ED) and the intensive care unit (ICU), accurate time prediction of clinically critical events is crucial to make a timely intervention for acutely deteriorating patients. Though there are needs for the timely decision-making, most reported studies make predictions in coarse-grained time resolution using electronic health records (EHR). Therefore, in this study, we propose an hourly deterioration prediction method over the future 12 hours using EHR for two representative critical events in ED and ICU, which are mortality and vasopressor need prediction. We use Mimic ED and Mimic 4 to extract 18 numeric features and chief complaints. To come up with our final model, we gradually add features with the best performance in the following order. Note that for each study, we select the best performing one using validation AURC and fix it for the remaining studies to assess the efficacy of the added component. Our study starts with the unimodal model to learn EHR numeric data. Then, with the best performing unimodal model, we search for the best performing bimodal fusion strategy to fuse EHR chief complaints to EHR numeric. Then, we compare several self-supervised regularization losses. Lastly, we explore several encoding strategies to encode the future EHR numeric. We will start with unimodal model search. For our unimodal model to learn EHR numeric, we compared GRUD, LSTM, vanilla transformer, and graph transformer. This figure at the right side here illustrates the scheme of our unimodal model. We used two-layer multi-layer perceptron with layer normalization and ReLU nonlinearity as an encoder here. Note that we make an hourly binary prediction for the future 12 hours as depicted here. In this stage, the vanilla transformer outperformed the other models in both mortality and vasopressor need predictions. Next, we compared three different bimodal fusion strategies. We compared multimodal ball transformer, which we call MBT here, multimodal transformer, which we call MT here, and bicross model tension transformer, which we call BCMAT here. For each fusion strategies, we experimented two different fusion locations, which are early and mid. Early fusion occurs after the 0th layer of the fusion transformer, which is actually before the transformer, whereas a mid fusion occurs at the 4th layer of the fusion transformer. Before the fusion, EHR text is encoded using the vanilla transformer with BERT tokenization. Note that how the figure at the right side here changed from the previous unimodal model. In this stage, the multimodal ball transformer outperformed the other in vasopressor need prediction, whereas the multimodal transformer outperformed the other in mortality prediction. Next, we compared three different loss functions for our self-supervised predictive regularization. We compared noise contrastive estimation, which we call NCE here, cosine loss, and L2 loss. For L2 loss with MT, we added the additional layer normalization for the output of the fusion transformer. Since L2 loss from the normalized context vector here is too large in its value compared to the supervision loss. In the results section, this additional normalization is shown to impact the performance much. As illustrated at the right side here, we compare the encoded feature signal instead of the raw feature signal as suggested in the original CPC paper. Note that this encoder here are all shared. In this stage, the L2 loss with the additional normalization outperformed the other in both vasopressor need and mortality prediction. Lastly, we compared three different structures to encode the future numeric for our self-supervised regularization. As illustrated at the right side of this slide, we first tried no encoder, meaning that we let the context vector from the fusion transformer directly predict the raw future numeric data. The encoding method experimented at the previous stage was originally suggested because of the high dimensionality of the raw data. Since our raw numeric signal is in low dimension, we tried omitting the encoder for the future numeric, as illustrated in this figure. This approach outperformed other variants in mortality prediction. The encoding structure depicted in this slide was already used as a default structure for the previous stage to compare three different loss functions. This approach outperformed other variants in vasopressor need prediction. As illustrated at the right side of this slide, we also tried modeling the aggregated future numeric. Note that both the encoder and the fusion transformer are shared for the past here and the future here. From now on, I'll discuss about the result. We select the best performing model with the validation area RC for each stage, which are unimodal model, bimodal fusion strategies, self-supervised predictive loss, and the encoding structure for the future numeric. With the best performing model from each stage, we move on to the next stage to accumulate the best performing component. Note that one of the important aims in this study is to suggest the fine-grained time deterioration prediction method. Therefore, we report not only the validation AUROC averaged over the 12 time slot here, but also the validation AUROC for each time slot. For the unimodal model to learn, the EHR numeric vanilla transformer outperformed the other. For the bimodal fusion strategies to fuse EHR text to the EHR numeric, MT and MBT, MT here and MBT here, outperformed the other for mortality and vasopressor need prediction. Note that the gap between the MT and MBT here is small in mortality prediction. The L2 loss with the normalization outperformed all other candidates for self-supervised regularization. Note that the huge performance gap here between the L2 loss with normalized and unnormalized context vector for the mortality prediction. For the mortality prediction, modeling the raw future numeric performed the best, whereas modeling the encoded future numeric excels in vasopressor need prediction. After selecting the best option for a unimodal model and the bimodal fusion strategy and self-supervised regularization method, we use a test AURC to compare their performances to assess if the added feature actually helps. In summary, both our EHR text supplementation and self-supervised predictive regularization turns out to improve the predictive performance in both tests. Specifically, adding the EHR text data to EHR numeric by bimodal fusion improves the overall and the far future prediction of the unimodal model. Additional self-supervised predictive loss further improves the overall and the far future prediction of the bimodal model by 0.02 and 0.031 in mortality prediction and 0.038 and 0.045 in vasopressor need prediction. Note that for the baseline unimodal model, mortality predictive performance degrades much as prediction times gets further in the future, unlike vasopressor need prediction. Though both our bimodal fusion and self-supervised predictive regularization improve the overall predictive performance for mortality prediction, they yield more improvement as prediction time gets further in the future, especially mortality prediction. In conclusion, we propose a fine-grained time deterioration prediction method using electronic health records for two representative critical events in ED and ICU, which are mortality, vasopressor need prediction. We show our fusion strategy for clinical note and numeric data. And self-supervised regularization method improves the predictive performance in a fine-grained time resolution. In addition, we show the importance of context vector normalization for L2 loss in self-supervised predictive coding regularization. We believe our method will advance timely intervention and effective resource allocation in the ED and the ICU with the improved and thus more trustworthy prediction of patients' critical events. Thank you very much.